this module, I will summarize what we have done till now in this whole course. In the first week, I talked about the failures of classical mechanics. I talked about blackbody radiation, and I talked about the Planck's radiation law, which was the first bold hypothesis presented before German Physical Society, and then how this particular quantization hypothesis was used to explain all those observations which was already there, but it was unexplained. Say it was a particle photoelectric effect was explained using this one by Einstein. Then Bohr's atomic model was developed, and the hydrogen spectrum was already known. That spectrum was explained using this one. Then the specific heat of monoatomic solid was not constant with respect to temperature. So again, Planck used this quantization hypothesis and explained that phenomena. So the first week was basically how the quantum mechanics came into existence. It was nowhere. It was a paradigm shift in the physics. So it came from it started from the Planck's hypothesis, and then it took next 25 years to mature into a full theory of quantum mechanics. Okay. 25-26 years it took to mature into quantum theory of quantum mechanics. Then in the next module, in the next week, I talked about that how do we apply, what are the principles of using these quantum mechanical theories, and that's called postulates of quantum mechanics. I started talking about. In postulates, I talked about 5 things, 5 postulates. The first one was about the wave function. The second one was about the operators. The third one was about the eigenvalue equations. The fourth one was about the expectation value. And the fifth one was the time dependent Schrodinger wave equation. And I talked in details about what is normalization, what is orthogonality, how do we normalize, how do you check the orthogonality conditions. Okay. So all these things we talked about. After giving you the principles, these are the principles based on which we applied Schrodinger wave equation to different systems. The next task was applying Schrodinger wave equation to different model system and different real system. So in the model system, I talked about particle in a 1D box. 1D box, free particle also I did, 1D box, then I talked about 2D box, then I talked about 3D box. This particle in a one-dimensional box, what we did was an infinite potential well, infinite potential well. Then a departure from this was that one of the boundaries is infinite, another boundary becomes finite. So I talked about finite potential barrier also, finite potential barrier also. Okay, and then I talked about that if the particle is moving in one dimension and in between you have a potential barrier of thickness T, then what will happen? So we talked about quantum mechanical tunneling. Okay. And I showed you that if you have the tunneling takes place and the particle goes beyond the potential barrier also, which is in contrast to any classical theory. Okay, so quantum mechanical results are always gives you something which you cannot think of in classical mechanics. So the tunneling phenomena we talked about, and thereafter the next model system was simple harmonic oscillator, which I talked about. And we derived when I say I talked about particle in one dimension, I talked about SHO means what we did is we applied Schrodinger wave equation to get a normalized wave function for the system, and we get the eigenvalue. So we got the eigenvalue also, we got the eigenfunction also, and what we got is potential energy of a harmonic oscillator is V plus half h nu, which you already were knowing because in IR spectroscopy you have done this formula. So we derived this relationship, and we also find out the wave function for this one for a beta divided by pi raised to the power 1 by 4 exponential minus beta x square divided by 2 for the ground state. For the other states also there is a Hermite polynomial also. So we talked about solution of simple harmonic oscillator. After doing this, we entered into another model system, which was rigid rotor. And in rigid rotor, since the particle is moving in a circular path, so what we used is Schrodinger wave equation in spherical polar coordinates. Schrodinger wave equation in a spherical polar coordinates, that is r, theta and phi. So we talked about r, theta and phi. How do we get the equation, Schrodinger wave equation, in terms of r, theta and phi. And then for rigid rotor, we did separation of variables and we got two different equations, separation of variables, and we got two different equations, phi equation and theta equations. We solved both these equations separately, phi equations also and theta equations also. Theta equations was a little lengthy, involving Legendre polynomial. So those of you who feel very much burdened with the mathematics of Legendre equations need not to go into the every steps, but you should know how, from where it comes. So I did all the solutions and I did it in a stepwise manner. All steps are there, but even then, if you feel issue with the mathematics involved, then you should concentrate on the physical interpretation of the results which I have given you, which these calculations gives you. Phi equation was very simple. It was very similar to the particle in a one-dimensional box, and we got an equation. Normalized solution is 1 by root 2 pi exponential plus minus im phi. This was the solution for phi equations. Okay, and what does it gives you? This m is actually a the magnetic quantum number, which again you know already, or you were knowing already. Okay, but the theta equation gives you energy value, again known to you, h square divided by 8 pi square I, j into j plus 1. You know the energy of the rigid rotor, which you have done in rotational spectroscopy. Okay, and we got from the theta equation we got azimuthal quantum number also. Azimuthal quantum number also we got. Okay, so having done rigid rotor, the two equations, phi equations and theta equations, then the next problem or the next system which we talked about was hydrogen atom. And I said you that in hydrogen atom solution, when you do separation of variable, you get three independent equations: phi equation, theta equation and r equation. These theta and phi equations are very similar to rigid rotor. So we did not do the solution again. We just copied it from the theta and phi equation solution from the rigid rotor, because it was exactly the same equation. Then we solved r equation in details, and I talked about the different wave functions for the theta and phi equations. When you combine this theta and phi part, phi depending on phi and theta depending on theta, then I said you this tells you the angular dependence of the function, and this is called spherical harmonics. And the r function, r depending on r, r NL, the solution of r equation gives you the principal quantum number. And here again in associated Laguerre polynomial is involved. So again I would say that if you have an issue with the mathematical derivations of the equations, you just read the textbook. There is a table which gives you the value of r functions, and you try to explain this in the physical terms, that if what happens to the when you plot a spherical harmonics, and what happens you plot a r equation, r part of the equations. How does you get the nodes in 2s and 3s as in contrast to 1s, that all radial nodes you get from the plot of r and L. So all this. Then we talked about radial probability distribution function also. Okay, and we explained the why 1s orbital and 2s orbital and 2p orbital orientations. Then I talked about what is why if you have y LM proportional to cos theta, then it gives you a pz orbital, and if for px and py you need to have a linear combination of the two functions phi theta plus phi plus and phi minus, okay, and that linear combination gives you sin theta sin phi and cos theta sin theta cos phi. So px and py function orbitals you get. So all these concentrate on the physical interpretation of spherical harmonics and the radial part of the functions. That's more important as a chemistry student. Mathematics also I have given you. If someone of you can do it, it's fine. But if you cannot do it, you should concentrate on the physical interpretation of these results. That how do you get these plots of radial distribution functions, or plot of angular plots, how do you plot theta and phi functions. So these are important things which I talked about. Having done this hydrogen atom, and since we have done the motion in the circular path, so automatically the concept of angular momentum comes into picture. And this angular momentum is again one of the very important concept in quantum mechanics. So I talked about in details about the angular momentum. In angular momentum I talked about commutator relationships. I talked about ladder operator. I talked about ladder operator. I talked about the eigenvalues of the angular momentum operator. And I talked about that how the component Lz when applied to phi m becomes equal to mh cross phi m, it gives you. So this is your eigenvalue, okay. And what happens when you apply L square to theta Lm, what do you get? Okay. So all this we talked about eigenvalues, okay. Then I said you why it is so that the value of m is limited to 2l plus 1 values, so that you get minus m and minus m plus 1 and so on. So minus m to plus m including 0, minus m to plus m including 0, okay. So why this limitations is there, this also we talked about in the angular momentum section. Then I introduced you with the spin angular momentum. This was all about orbital angular momentum. Then I introduced you with the spin angular momentum, and I said you that spin angular momentum is purely a quantum mechanical property. A spin angular momentum does not have any classical counterpart. We cannot say that as the earth is rotating on the axis, so electron will also rotate, nothing like that. There is no classical counterpart of a spin angular momentum, okay. So we talked about the commutation relationship with respect to spin angular momentum also, and then I said you that when you have more than one source of the angular momentum, whether it is 2 electron or whether it is electron, a spin and the orbital, then how do they combine together? So addition of angular momentum we talked about. All these are vector quantity angular momentum. So how do they add together? And for in this adding together, we talked about LS coupling, or called Russell-Saunders coupling. This gives you different spectroscopic term symbol. So again in term symbol I talked about the term symbol of P2 configuration and D2 configuration, and I also talked about the term symbol of non-equivalent case. So if you have a helium atom like this one of the helium atom electron is in 1s1 and another is in 2s1, then what will be the term symbol of the system? So equivalent electrons, 2 electrons which is present in P was equivalent, 2 electrons which are present in D was equivalent. So how do you find out the term symbol for equivalent electrons and non-equivalent electrons? This also we talked about. Having finished with the angular momentum, then I said you we come to the approximation methods. And why do we approximate? Because I said you for larger system the potential energy terms become big, and this complicates the situation. You have nucleus also, you have electron also, there is internuclear repulsion, there is inter-electronic repulsion. So all these terms cannot be when accommodated into the Schrodinger wave equation, complicates, and the solution becomes impossible, not feasible for the Schrodinger wave equation. So for those systems for which the analytical solution, in fact, going beyond hydrogen molecule does not give you the solution. The moment you go for helium or lithium or beryllium, you cannot get the solution of Schrodinger wave equation for larger atoms. So you need approximations. Okay, if you cannot get the exact solution, then go for the approximate solution. And for that, the quantum mechanics has two different approaches. One of the approach is variation treatment, another is variation approximation methods, and another is perturbation approximation method. So I talked about variation methods, that you take a trial function and then you minimize the energy, and from the minimized energy you get the wave functions and the minimum possible energy. So taking a trial function was first step, then getting the energy value for the trial function was second step, and then from this energy value, minimization of this energy gave you the energy which is very close to the actual value. In fact, what we did was the trial function which we have taken for hydrogen atom. If I remember, it was exponential minus CR, which is same as you get from the Schrodinger wave equation solution for the hydrogen atom. And I talked about those solutions which were already known, because I wanted to tell you that variation treatment, if you do for a system, then then actually what you get is the result which is very close to the actual system. Okay, so we talked about variation treatment of hydrogen atom. We talked about variation treatment of particle in a one-dimensional box also. Okay. And thereafter, I introduced you with a system for which you can get, we can take a linear combination of the two trial functions, and that is called linear variation treatment. And we got the secular determinant from this linear variation treatment. Okay. So having done this up to secular determinant, then I shifted it to perturbation theory, and I said in perturbation theory has the limitation that you can deal with a system for which you have a very closely related system for which the solution is already known, and you compare between the two systems. One which is for which the solution is already known is called unperturbed system, and your system on which you are working, which is a perturbed system, and for this the solution is not known. So you have to have a system which is unperturbed in order to do the perturbation theory. And then I tell you that in perturbation theory has different levels. That could be a first order perturbation, it could be a second order perturbation, and how to find out the first order perturbation energy, second order perturbation energy, and all this we talked about for non-degenerate system. I said perturbation theory could be time independent or time dependent. When time independent perturbation theory I talked about, it could be for degenerate system and for non-degenerate system. So the first I talked about non-degenerate system, and from non-degenerate system we calculated En1 value and psi n1 value, first order correction to energy, first order correction to wave functions. Then also I gave you the relation for second order correction to energy and second order correction to wave functions. Okay. So having done this non-degenerate perturbation theory, I moved on to degenerate perturbation theory, and I said you that both have different approaches. Okay. So degenerate perturbation theory also I did, and then the third one was time dependent perturbation. This also I talked about. In time dependent perturbation, I said you that when an electromagnetic radiation falls on the molecule goes from the ground state to the excited state. So there is a time lag between this one, and this phenomena can be dealt only with the time dependent perturbation. Here the perturbation is the electric field of the electromagnetic radiation which is interacting with the molecule. So this is the perturbation, and from this perturbation I talked about the probability of molecule being in the excited state, and this was proportional to the transition moment integral which I talked about. Okay. So this was all about the three perturbation theories: degenerate, non-degenerate, degenerate, and time dependent perturbation. Okay. After finishing this perturbation theory, again I went back to valence bond theory, and in valence bond theory I talked about the approaches which is used for the hybridization of the molecule, and how do the central atom orbitals hybridize to give you a specific shape of the molecule. So I talked about all sp, sp2, sp3 hybridization and their wave functions. How do we find out the coefficients? How do we find out the orientations? So this was the topic in the valence bond theory. Then again, for dealing with the molecule, I talked about H2 plus molecule ion in molecular orbital theory. Then I talked about molecular orbital theory, and H2 plus molecule ion I did in details, giving you using the secular determinant. I talked about how do we find out the bonding molecular orbital energy and anti-bonding molecular orbital energy, and what is the difference between the energy, how do you get the wave functions, how do we normalize the wave functions. All those details I talked about H2 plus molecule. Then an extension of H2 plus molecule, I said all diatomic molecules. All diatomic molecules means H2 molecules up to N2 molecule, F2 molecules we talked about that. What is the molecular orbital diagram and how do the orbital overlaps, which orbital can overlap to give you molecular orbital, which cannot interact, which cannot interact. So all these were the criteria for linear combination of atomic orbitals. All this we talked about in the diatomic molecule section. And for that matter, I talked about a triatomic molecule also, BeH2 molecule, and then I said you that we will talk about the thereafter we talked about the HMO, Huckel molecular approximation, HMO, Huckel molecular orbital, and in this Huckel molecular orbital I said you that Huckel made a very drastic approximations, and with those drastic approximations he was able to tell you the energy level diagram of conjugated molecules. And in this HMO I talked about ethylene molecule, I talked about propenyl systems, allyl systems, cyclopropenyl system in fact. So let me write it. From ethylene molecules, I talked about allyl system, then I talked about cyclopropenyl, then I talked about butadiene, then I talked about, from butadiene I talked about benzene, cyclobutadiene, cyclobutadiene, then I talked about benzene. So all these systems, in case of we talked about in the HMO, we found the electron density, charge density, bond order in each case, and we also find out the wave function for the different molecular orbitals created by HMO approximations. Okay. So that was the end of your course, but at the end of the course, since it was all theory, so I requested one of my colleagues to talk about the application of quantum principles in designing the devices or developing the materials. So Dr. Palasuddin talked about that how do we apply quantum mechanical principles in the material sciences, in nanomaterials and quantum dots. So that was also added. But how do we go beyond this one? What I have done is with the foundation of quantum chemistry. What I did not talk about is also very important. When you apply Schrodinger this quantum mechanical principles to higher molecules, what you should know is self-consistent field theory, which is very important. Hartree-Fock self-consistent field theory, that you will have to do. I have given you the foundation and you can go ahead, because otherwise I will keep on doing and your course will be very lengthy. So these are some advanced topics which I have not covered. HFSCF you should do. You should talk about several empirical methods which is available for quantum mechanical calculations. So empirical methods, you look at this one. One thing should be very clear in your mind, that analytical solution of Schrodinger wave equation was available up to hydrogen atom only. Beyond this, it is all approximations. So some empirical methods also developed, and then the another concept which was developed by is DFT. That DFT calculations also. All these calculations which you do now, you don't do these days. You don't do calculations on the pen and paper. You have software developed for this one. And these calculations, which is based on the quantum mechanical principles, are called ab initio calculations. Ab initio calculations. And we have software for this, and the most famous software is Gaussian. It's paid software. Gaussian is the most famous software. Then free also, we have Orca as the free software, others also. Okay. So Gaussian is most widely used for the ab initio calculations. Ab initio calculations, even with the Gaussian, if you increase the size of the system, becomes very difficult. Okay. So, for H2 molecule, quantum mechanics is applicable. Beyond that, approximation does very good work. What happens to very large molecule? If you talk about protein molecule, DNA molecules, can we do ab initio calculations? No, we cannot do. Then what we do is that we combine both classical and quantum mechanics, and we develop a new method for simulating these larger structures called molecular dynamic simulations. Molecular dynamic simulations. So, the idea of this course is to give you a foundation for learning these objectives, for running the Gaussian, for knowing what is molecular dynamic simulations and how do we simulate larger molecules. This course is a fundamental course, is a core course for everywhere. So, you learn whatever you have learned in this course should give you a foundation for learning these HFSCF, empirical calculations, DFT, molecular dynamic simulations, and all the advanced topics. Hope I have done justice with this course. Thank you, and I end here for this course. Okay, thank you.